power for almost, well, I guess, 3.5 years now. Before that, I was at another, utility consulting firm, and I guess overall it's been almost 5.5 years, or almost 6 years in the industry now. So pretty crazy. I graduated from UMaine ECE in 2019. I was classmates with Mr. Rob there. Um, yeah, and it's been a great time ever since. So I guess we'll jump right in. I won't have my camera on the whole time, otherwise I'm gonna be looking off to the side. And I don't know, you guys don't need to be looking at the side of my head the whole time. So feel free to turn yours off too if you want. And I guess I will say thank you, Ryan, for starting the recording. And just so everybody knows, we are going to record this for future reference for everybody. So I'll turn this off. Let me share my screen with the presentation, and we will get rolling. Oh, I went to the wrong screen. That's great. Okay. So, like I said, I will be doing our presentation on relay one lines, or I guess this first one is one lines. And let's scroll through here. Okay, here we go. Let me just make sure this is the right one real quick. Sorry, everybody. Okay, yeah, I think we're good. So, what is one line diagram? We've got a couple bullets here that kind of describe what it is, but it's really the simplest way to describe, how a substation functions and, what it looks like, what the configuration is. I guess our bullets here are preliminary one lines are developed for planning, budgeting, and preliminary engineering. And one line is typically finalized during the preliminary engineering phase. So, in the work we do, as an engineering consulting firm, we work with, electric utilities, and we help them with, whatever problems they may have. So early on, when they decide that they have a or they find that, a piece of their equipment has failed, the first place we look is the one line. And, again, because it's so simple, it's so easy to see how the substation is configured. So when they're going to plan out what they want to do and create a budget for it, it's really easy to say, okay, well, this breaker in the station failed. We're going to replace it. How much does that cost? How do we plan for that? And then, among these other bullets, we have AC schematic diagrams, DC schematics, wiring diagrams, block diagrams. Those are other types of drawings that get developed during, our detailed engineering phase that we call. And I think, you'll go over some of those in the following presentations, hopefully later with Ryan in this one. And I apologize if I'm going fast through things, but again, we have a lot to get through tonight. So types of one lines, typically we see two different types. We see a power one line and a relay one line. So power one line is mainly focused on the primary configuration, and I guess by primary we mean major equipment. So you'd see transformers, circuit breakers, capacitor banks, switches, and along with those you'd usually see ratings. So typically there's a continuous current rating associated with a piece of equipment. So like a breaker, you'd see something like 1200, 2000, or 3000 amps. Same thing for a switch. For a transformer, you'd see information listed like the MVA that it's rated for, maybe the percent Z that it's rated for, some cooling information, things like that. The other type of one line we have is a relay one line where, maybe they don't necessarily show all of that, rating information. Maybe the physical configurations of less importance, but mainly what the relay one line is for is to show the relays that are being installed and, maybe CT connections, PT connections, CT and PT ratios, zones of protection, things like that. Other common types of one lines are switching one lines, area one lines, communication one lines, AC station service, and DC station service. So another one I will mention is maybe like an outage one line where they show what lines or breakers or pieces of equipment will be taken out of service for an outage for construction or something like that. So yeah, just a couple extra other types of one lines. The purpose of one lines, they do both serve similar purposes. Again, the power one line kind of just serves as the blueprint for the physical configuration, and the relay one line, more or less serves as the blueprint for the protection configuration, right? I guess our bullets here say their main purpose is to show a single line representation of the substation, detail ratings of equipment, like I mentioned, presenting a functional solution that can be built. So sometimes our clients come to us with problems that can't be solved with just modifying an existing station. They need to install a whole new station. So that could be our functional solution. And again, highlighting the major equipment to be installed, with the ratings, that typically, our client will give us desired ratings that they want to hit. So ensuring that the equipment on the one line shows that it is properly rated for those ratings, that's pretty important. And then diagrammatically represent the scope. And by that, we mean, if our client gives us, a scope of work to base our designs off of, the one line diagram needs to reflect that, right? If they say they want to, we'll get into the specifics of this later, but if they say they want a 6-breaker ring bus, and then our one line only shows, a 4-breaker single bus, we screwed up somewhere, right? So pretty important to have your one lines correct. This is an example of a power one line. You can see, it shows major equipment. I guess, I don't know if you can see my cursor or not, but looking at the top left here, we have a PT, a potential transformer. We've got a switch here, another switch, circuit breaker, another switch. Oh, I messed up. A switch, and this little M in a circle means it's motor operated. So, the switch gets installed, and then instead of having to go out there and crank it open, there's a button you can push, and there's a motor that will open the switch. Another big one, there's a transformer right here. And of course, all these symbols get repeated all over the place. So there's some pretty typical symbols. Again, breakers, switches, you'll see those everywhere. Transformers, this is a regulator. You don't see that very often, but yeah, just a good example of a power one line. And this here is a relay one line diagram, and this is actually a relay one line diagram based off of that power one line we were just looking at. So if I go back a second, I know the text is small, but if you look here, it says 69 kV to Apache generation station. We have, switch MQ20, breaker MQ10, switch MQ30. If we come here, this is our relay one line. We have, that same line name, switch MQ20, breaker MQ10, switch MQ30. But along with that, we've got a lot more information on here, right? Where these are the CTs that are associated with the breaker. We see our connection to the relays, right? We do see the relays themselves. And then on this particular relay one line, we actually see these, I guess I don't even know what to call them, but these trip and lockout lines. So we can see exactly what functions these relays are doing. So there's, a trip line for tripping the breaker from some of them lock out the breaker, and, those are all over the place. I think this is a pretty detailed relay one line. Some of them don't show this much information, but still a great example of a pretty well put together relay one line. Next, I think we'll get some one-line symbols. I think we go through, quite a few of the major ones here. So there's two different types, major types, I guess. So we have ANSI symbols and IEC symbols, and I guess the difference there is US really uses ANSI, and then Europe uses a lot of IEC symbols. So it's pretty important making sure you know which catalog you're working with, right? If your client or your utility is working with ANSI and you're running with IEC symbols on your drawings, obviously that's a no-go, right? And I mean, down here we can see, and these are three different types of symbols for just a current transformer, right? There are three different types of current transformers, right? This looks like a standalone CT, like it's maybe mounted on its own structure. Um, looks like somebody's drawing it. I'll add them real quick. Like a CT mounted on its own structure. This CT is a bushing type, meaning it would be installed on the bushing of a transformer or a circuit breaker or some piece of equipment like that. And then this third one would be a slip-on, meaning it, I guess, it kind of explains itself, right? It kind of just slips over whatever you're trying to install it on. So again, very important to know what symbol you're working with. Important confirmed standards, I guess we kind of just mentioned that, but I guess I did mention IEC versus ANSI, but even across clients, right? This particular client here, they like to show breakers and the switches like this, but for a similar type of breaker and switches, the next utility likes to show them like this. And this is a transformer for that first utility. This is a transformer for the second utility, right? So they all like to show them differently, and it's just important to know how they like to show it. So here's some of the ANSI symbols. I guess these ones kind of look old, but CTs with their polarity markings, connection symbols, so like Y or delta for a transformer, basic context, so like a normally closed, normally open contact, and there's a couple different ways to show that. Relay operating coil, circuit breakers. Again, these ones are older, so unless it's super basic, I think utilities kind of have their own way to show these, but I think we look at some of those now. Here are the ISO graphic symbols, two windings voltage transformer, single phase voltage transformer, just different ways to show the transformer. Again, kind of getting at, there's a lot of different ways to represent a single piece of equipment. Let's step through power one line. So this was a project we did pretty recently that kind of had everything. Honestly, it had transmission lines coming into the station. It had breakers. It had transformers. It had capacitor bank. It had reactors. It had everything pretty much. So I guess we'll take a look here. So the first item we're going to look at is a breaker. So a breaker, for those of you who don't know, I guess getting real basic here, it's just an interrupting device. These pretty much act just like the breakers in your electrical panel, right? Maybe the current flowing through them is too high, the relay reads that, and the breaker trips, right? So it's just an interrupting device, and there's not much more to it than that. Usually what the utilities like to do is they'll put disconnect switches on either side of the breaker in case the breaker, needs maintenance or it fails. And well, I guess the idea here is they're for maintenance, right? So if it fails, it would obviously need maintenance. So say the breaker fails, they open up the switches so the breaker isn't energized anymore because this is being operated at 138,000 volts, which I don't know about you guys, but I don't want to be touching that. So they'll open the switches and then they can get into the panel, they can replace the breaker, they can do whatever. Usually, at this voltage class, you see, 4 sets of CTs, and that's what each one of these represents. That's a set of CTs. So that, I guess what I mean by that is there's going to be one CT per phase per set. So this one symbol here would be one CT for each phase A, B, and C, right? So I guess that may have been a confusing way to explain it, but this is a pretty typical arrangement for a 138 kV breaker. You can, at the higher voltages, when the breaker bushings get longer, sometimes you see 3 per phase or 3 per bushing per phase, I guess. I'm saying that wrong, but you'll see, instead of 2 on each side, you'll see 3. At the lower voltages, sometimes you'll just see 1. But yeah, that's kind of a typical breaker installation right there. Here we've got a line terminal. This first symbol here, this is a switch. And again, this is the circle with the little M in it. So this one just happens to be motor operated. And I guess for those of you who may have joined late, what that means is, instead of having to go up to the switch and crank it open, there's a motor. You can just push a button on it and the switch will open. This piece of equipment right here is a surge arrestor. And what that's for is if there's like a lightning strike out on the line, the voltage from that lightning strike, or I guess the current voltage impulse, right, won't travel into the station. It will hit this arrestor. And this arrestor almost acts like a voltage transistor or something like that. So when the voltage gets too high on this top terminal, it'll start conducting to ground. So then, whatever happens from that lightning impulse will just go to ground and not into the station to our more expensive equipment. This third piece of equipment, this is a CCVT, and that is a coupling capacitor voltage transformer. These are typically used at voltages higher than like 69 kV or 115 kV. And really all they're for is to provide monitoring, safe monitoring potentials to the relays. The high side of this CCVT would be connected at, 138 kV, but, our relays only want to read, 120 volts or 67 volts, right? So that's what these are for, so the relays can monitor the lines better. Transformers, these are big power transformers. Again, I was mentioning earlier, there's usually some good info here. So we've got, 54, 72, 90 MVA. That's, the thermal rating of the transformer. This ONAN, ONAF, ONAF, that's the cooling sequence of the transformer. It's got the impedance of the transformer, things like that, right? So usually what we show on the one line here is, we show H1 for the high side connections. We'll show X1 for the low side connections. And if it does have a tertiary winding, just a third lower voltage winding, usually there's like a Y bushing or maybe some other character for it, but usually you see Y. On here, we have these little symbols. So the H and X bushings, those windings are Y solidly grounded, and the tertiary is a delta connection, and that's pretty typical for these auto transformers. This connection here, this is our neutral for the transformer, and calling it H0, X0, or just H0, just X0 is pretty common. And usually this, or always, this should just be grounded, right? If it's Y solidly grounded. Here we've got PT. These are used at less than 69 kV, and they still serve the same purpose as a CCVT. It's just providing safe voltage levels for the relays. This piece of equipment, capacitor, and this is actually a capacitor bank. This provides VARs to the system or absorbs VARs. I always get it mixed up, but it's supposed to help with stability in the system, right? You don't want too many. You want it as close to zero as you can get, right? So with some utilities will install capacitor banks, or they'll install reactors depending on what the system needs. So that's this symbol. I mean, you guys have probably seen capacitor symbols all over the place, but these aren't like little tiny capacitors you stick in a breadboard. These are big cans that get stacked together on a big, 15-foot tall structure. Where'd my mouse go? There it is. This symbol right here, this is another symbol for a CT. Again, this isn't like a bushing CT like we saw with the breakers. This is a standalone CT that's just kind of off on its own. It's not installed on a bushing. It's not slipped over on anything. Usually they're installed on structures by themselves. And then again, this symbol is a current limiting reactor. So you saw this on here, so the current flowing into here doesn't jump to dangerous levels, right? If there's a fault or something like that. Okay. So I guess this is kind of getting into the project development stages, right? Where where does the one line come into play, right? So there's a few different stages that we talked about. There's conceptualization, project planning, development, execution. So conceptualization, right? A lot of times for utilities, this comes pretty easy, right? If a transformer blew up, right, you don't really need to conceptualize what the project is, right? You need to replace the transformer. Other times, it's a little more difficult. The utilities have to run a lot of studies. They have to do a lot of power flow analysis to understand what needs to be installed in the system to make it run more, or run have more stability, right? So going back to those capacitor banks on those reactors, they don't just throw those in there all willy-nilly, right? They choose where to put those very carefully. Project planning, usually this comes after, figuring out, what they want to do something, or the why they want to do something, and then the project planning is what they want to do, right? So they say, okay, the system, has too many VARs on it, right? What are we going to do about that? Well, let's install a capacitor bank, right? Development is the how. Like, how are we going to do that? How are we going to install this capacitor bank at a substation? Is there enough room? What capacitor bank should we use, right? And then execution is, design and construction. Maybe I got ahead of myself here a little bit, but yeah, identifying the optimum solution, feasibility studies, that's kind of part of the power flow analysis, things like that, interconnection studies, between independent system operators or between utilities themselves, and then environmental impact assessments. Environmental impact ends up being a huge driver a lot of the time of what a utility can or cannot do. So I guess, let me go back to this one line real quick. Looking at this one line, this configuration was kind of chosen for us by the utility, right? They knew what they wanted based on some of their, studies, some of their analysis, right? And they determined that this is what best met their needs. But, how do they figure that out, right? How do they decide what configuration is best? So there are, a lot of the times there are numerous arrangements for a given substation. Who knows what's best, right? Sometimes 2 or 3 configurations might be best, but there's a lot of things that go into that, right? So cost is usually a big one. Reliability and safety are big ones. Again, environmental impact is usually a big one. Available land, like actual physical land, parcels of land are huge ones recently. So things like that go into deciding what configuration could be best. Oh, and here we go. Station size, reliability, operability, constructability, maintenance, outer sequencing, customer constraints, right? So kind of those things that we just listed off. Now we'll go through some of the different station configurations. This first one is a straight bus. And all it is straight bus. It's pretty straightforward. It's not very reliable, right? Say, this bus number 1, if there's, a lightning strike on the bus and there's a fault, right? Your breakers would trip, so you'd lose line 2, transformer 1, and line 1, and this breaker would trip as well, right? So for one fault, you'd lose, all 3 of these lines or pieces of equipment. Yeah, here we go. I guess advantages and disadvantages. So again, it's not very expensive. So, maybe that if your utility is looking for something cheap, quick and dirty, not too bad, easily expandable and smaller footprint. But again, not very reliable, which seems to be the name of the game these days. A ring bus, we do see this one quite a bit. You can kind of see it's built in a ring, right? Where for every, node, there's a breaker on either side. And so say we had a lightning strike on line 2, or there was a fault on line 2, right? This breaker and this breaker would trip, but we wouldn't lose transformer 2, line 1, or transformer 1, right? We'd only lose line 2. So much more reliable than the straight bus. They are typically used at, over 69 kV. They're a little more cost effective than some of the other options we have that are more reliable. They are usually a smaller footprint. and like we just mentioned, a fault exposure is limited. The only problem here is a breaker failure situation, which if we go back a slide, so let's say we had a fault on line 2, this breaker and this breaker are meant to trip, but this breaker fails to trip, then we'd have to trip this breaker as well. So then you lose line 2 and transformer 2. So that's a little disappointing, right? That's a disadvantage of the ring bus, and again, it is a little more expensive than the straight bus, but still more reliable. This is the breaker and a half configuration. What this consists of is there'll be a bus on either side. There'll be 3 breakers between the buses, and uh, lines or transformers or things like that coming into the nodes between the breakers, but not onto the buses. And it's called a breaker and a half because it's like these pieces of equipment are sharing this middle breaker, so they quote unquote own this breaker, and then each one of them has half of that middle breaker. You typically see these probably as much or maybe a little more than the ring buses. It's usually pretty costly, and usually the client wants it to be expandable. So usually what you see is when you first build one of these stations, you'll just build maybe these 2 rungs, but then they want the station to be able to expand to in case this whole setup, right? So it ends up not being super expensive right off, but building out for or expecting to build out for the future can be pretty expensive on some of the site work, things like that. The same disadvantages or same first disadvantage as a ring bus. A breaker failure can take out 2 nodes, and where it gets really tricky is, say, like if you didn't have this breaker here, this bus tie breaker, and this breaker failed on a trip here or on a fault here, you'd have to clear all of these breakers, right? So it can end up being a little funkier if you don't have it set up correctly. But I think the consensus is this ring bus is more reliable than the straight bus. The breaker and a half bus is more reliable than the ring bus. And finally, the double breaker double bus is more reliable than the breaker and a half. So here, each line or transformer has 2 breakers dedicated to it instead of just 1.5, like the breaker and a half. So, just with that logic, right? This one is already more expensive than the breaker and a half, by a power of 2 divided by 1.5, right? So, you don't really see these as much as the breaker and a half. They are the most reliable, but again, they end up being the most expensive, and they do have a large footprint, just like the breaker and a half does. So the best advantage here is a breaker failure scenario will never take out 2 nodes. So if you have a fault on a line, it will never take out another line. But again, just very, very expensive. So conceptual design deliverables. So when we talk about conceptual design, that usually means something like the very first phase of design we get into on a project. So these are some typical items that we would submit to our client is, like a 1-line diagram that we just talked about, GA drawings, general arrangement drawings, which is like a top-down view of the station, civil grading plans with how they plan to move the dirt around at the site to make it flat for the substation equipment, design criteria, material list for the major equipment, some cost estimates for the equipment or the whole substation. Those are some things we would give to our client. Here's some more examples. Here's a double breaker, double bus, 1 line. You can see, right, we've got lines coming here, lines coming in here. And I guess just for proof of concept, right, if, there was a fault on this line and this breaker failed, this breaker and this breaker would trip. This one fails, right? You could just trip all these breakers and you wouldn't lose any of the lines because they'd be fed from this bus, right? So there's a double breaker, double bus. This is a general arrangement. This is a top-down view of the station. So you can see that, this footprint, I guess just on the PowerPoint, maybe it isn't as magnificent as I think it is, but these dimensions on the side, right? This is 600 feet by 500 feet. So 6 football field, or not 6 football fields, but like what, 3 football fields long by 2.5 tall, right? That's pretty big. Here's another one. It's kind of just placed in, our clients like to see this, the station's placed in Google Earth. So we end up doing that a lot. This is another double breaker, double bus scenario. This one's a breaker and a half. Again, you can see here's our bus on the side, our other bus, 3 breakers in between, and our lines leaving. And here's the general arrangement for that. There, right? We've got our bus, breaker, breaker, breaker. You can kind of see the lines. Maybe hard to see on the PowerPoint. Here it is in Google Earth again. I'm gonna be honest with you, I'm not really sure what that one is. Here's another general arrangement though. Just wonky configuration where they had to do some funny stuff with the buses, but still, if you could see down in there, they did a breaker and a half for the low side. I guess you can't really tell. Maybe this is also a breaker and a half for the high side. I guess that's it for just the one-line presentation, one-line part 1. I guess that took a little longer than I thought. Any questions on one-lines part 1? I know I kind of zoomed through it. All right, great. Let's roll into relay one-lines. I'll probably be pretty quick with this one, so Ryan has some time for his schematic presentation. So I guess I'll mention before we get into this, if there's any questions on one-lines, feel free to reach out to me directly, or give me a call if you're really feeling passionate about one-lines. But yeah, we'll try to get through this in 10 or 15 minutes. It's 30. So relay one-lines, I think we kind of mentioned them before. It's, instead of the blueprint for the physical design, it's the blueprint for the protection design. So a key to a great relaying one-line is a correct representation of the physical power one-line. A lot of the time, you just pretty much take the the physical one-line or the power one-line, and you keep the same configuration, the same orientation, and you just add your relays on it. And I think those make the best relay one-lines. Another item is your CTs and your PTs are represented properly, right? We looked at all the different symbols you can have, and you want to make sure you're using the correct one. Your relays are connected properly. If you don't connect your relays to the correct CTs or the PTs, or you connect them to the right CTs and PTs, but you connect them, maybe reverse polarity or something like that, you're going to have misoperations. Your phasing is accurate. That's a big one. You want to make sure, phase A is going to phase A, not phase A going to phase C. You want to make sure you don't have any gaps in your zones of protection, which I think we'll get into a little later in the presentation. And you want to make sure your breaker failure trips the correct breakers, which we'll also get into a little bit. So this is that same relay one-line we were looking at before. Again, they literally took this one. I would actually argue probably isn't built the best, right? Because this configuration or this orientation isn't the same as the power one-line, but there's so much relay information on here. They probably had to do some funny stuff. So concepts of relay operation, this would be the primary equipment, your high voltage equipment. So your 138 kV bus, your circuit breaker here. This would be like a bushing CT or a standalone CT or a slipover CT that's reading the current through the bus. A typical, secondary winding of a CT is, 5 amps, maybe you have 3,000 amps on the bus, but your secondary winding would be 5 amps. Your relay is reading that. And if the current in this winding gets too high, it trips the breaker, right? That's kind of the very basics of relay operation. Again, it's very similar to, the breakers in your house, right? If you have your, maybe your electric stove and your microwave and your air fryer going all at once, your breaker's probably going to trip because, you know, it's reading too much current in this coil, and it trips the breaker. So CT polarity is super important. This is how you know you're connecting your relays properly. And this polarity dot, it's actually a physical characteristic of the current transformer, and it's determined by which direction the coils are around the core. So, you know, if we want to measure the current, you know, going in the right direction, you know, we want to make sure we have, one, the CT installed properly, and then two, we want to make sure our leads are connected to the CT properly. Some good ways to screw up a CT circuit is leaving the CT open. And I guess the reason behind that is, right, the CT is trying to maintain a certain amount of current, or a certain amount of current going through the secondary winding, right? So if the resistance is set and the current is pretty well set, you know, the voltage is what's going to change here, right? So if you leave this open and you don't short it out when it's not being used, the CT, you know, theoretically, is going to try to pump the voltage, you know, from between these two terminals up to as high as it can get it. And what ends up happening is it blows up, and, you know, it ends up being very dangerous. And I guess it happens a lot, right, where people just forget to short these out, but it can cause some catastrophic instances. Using the incorrect CT ratio. So if the CT isn't wired properly, and say you're working with a 3,000 amp to 5 amp ratio, but your relay is expecting it to be 1,200 to 5 amps, you're probably going to have some relay misoperations due to it reading the wrong current. Again, we just talked about connecting the wrong polarity. It is current, so you want to connect things in series and not parallel. Otherwise, you're going to be reading, you know, a split current. I guess this one, maybe I get rid of that because that one doesn't really make much sense. But connecting the relay to the wrong CT, right? If you connect it to the wrong CT, maybe you have a gap in your zone of protection, or again, maybe you connected to a CT with the wrong ratio, right? A big one is sometimes these CT circuits. Let's see if we can find a good one here. So this CT right here, maybe that's not a good way to do it because you guys probably can't see that. But sometimes these CT circuits have a lot of relays on them. You know, maybe there's 3 or 4 relays on the same CT circuit. You don't want to install a bunch of grounds on there because these relays might be far apart. You know, they might be in separate control houses, things like that. And if you have grounds that are far apart, there's a fault in the station, you know, there's a pretty good chance you're going to have a potential difference between the grounds, and that could cause some relay misoperations. So installing one ground on the circuit is, you know, kind of standard operating procedure. Potential transformers, these are our CCVTs or PTs, things like that. And again, the high side, you know, that there's a tap up here that would, you know, connect to the 138 kV bus, 345 kV, whatever you're working with. And then, you know, there's some transformation that goes on in here, and you'd have some 120 volt or 67 volt connections down in here for the relays. Ways to screw up PT. Again, you know, CT, don't leave it open. PT, don't short it, right? Same ideas. But, you know, this is voltage versus current, right? Again, using the wrong ratio, connecting the wrong polarity. Same things you can do wrong with the CTs, you can do with the PTs, right? Zones of protection. So a zone of protection is monitored by a relaying scheme, you know, and a zone of protection is usually determined by what you're protecting, right? So a zone of protection for like a transmission line is going to look different than a zone of protection for a transformer is going to look different than a zone of protection for a bus, right? And they use different relays, they use different, you know, tripping schemes, things like that. You know, these are the big ones: differential protection, overcurrent protection, and distance protection. Those are what we see a lot of the time for, you know, typical pieces of equipment. So, you know, this kind of is just a very generalized way to show this, but right, we have a generator over here. connected to a transformer, a step-up transformer with a high side breaker. To protect our generator, we'd want our zone of protection to wrap the generator, the transformer, and the breaker. Because if you want to protect your generator, you need some kind of interrupting device, right? Which would be this high side breaker. Well, you want your interrupting device to be in the zone of protection as the same zone of protection as the piece of equipment, right? So for protecting the generator, we want to trip this breaker, keep the breaker in the zone of protection. We're protecting the transformer. We need an interrupting device. We have this breaker in our zone of protection, right? We have this bus we want to protect. We want to wrap these breakers to protect the bus. We have a line right here. I think you guys get it. It's kind of the same concept. Now, again, this is a very simple way to look at it. Some of these zones of protection, especially generator zones of protection, transformer zones of protection, get very complicated. So this is the one line we were looking at in the part 1 presentation. You can see here the zones of protection are drawn in. So the blue is for lines, the green is for cat bags, the red is for the transformers. So you can see the blue. Let's just focus on this transmission line heading out. I know it's kind of hard to see, but you can see this line comes in between these two breakers, right? So these two breakers are the interrupting devices to protect the line. So we wrap those two breakers in our zone of protection. And that way, the relaying for this line trips those breakers to interrupt any faults on this line, right? The transformers are a little different, right? Because it's not just, the two breakers and the line we're worried about. We're worried about this tertiary winding. There's all sorts of internal things to the transformer that need protection or do the protection for the transformer. But in this case, for the high side, we connect in between these two breakers. So we wrap those two breakers. And on the low side, we have this series breaker. So we wrap that breaker, and our protection needs to cover the tertiary stuff as well. So that's our zone of protection for the transformer. And then the cat bag is pretty straightforward. We have our high side breaker as our interrupting device. So our zone of protection just covers that breaker for the cat bag. System separation. This ends up being a big deal for stations, usually over 115 kV. What that means is utilities need some redundancy, and that's to maintain a certain standard of reliability in their stations and their systems, right? So there's things that should not be shared between these two independent systems of protection. And usually what happens is there will be two relays doing the same function. So for a bus zone, right, you'd actually have maybe two of the exact same relay doing the exact same function, tripping the exact same breakers, but it's really just to maintain reliability. So there's a couple things that are required for system separation. There's a couple things that are, I guess, suggested, and then a couple things that maybe utilities just don't follow. So you'll see like they call them like system 1 or system 2 or system A and system B. So system 1 can't connect to the same CTs and PTs as system 2. So on our breakers, I guess here, there's two sets of breakers on each side of the breaker. So system 1 would connect to one set, system 2 would connect to the other set. Same with the CCVTs. Usually there's two secondary windings that you can use. And like I was just saying, a lot of the times you'll just have two redundant relaying systems. So you'd have two bus relays, again, doing the exact same thing. Two separate battery banks for real system separation, because you don't want one battery bank to fail and to lose all of your protective equipment. Trip coils in the breakers. A lot of breakers just come with two sets of trip coils, expecting there to be system separation. Separate cabling from the equipment to the control buildings. I guess we have relaying twice, and then there are, like I was mentioning, there are a few exceptions and ways to mitigate issues. So this is actually what I was just kind of looking at on the other drawing, but here we've got, this relay right here, and I guess this box is representative of a relay. This is a separate relay. This is a separate relay. So what we have going on here is, this green and this blue. This is our zone of protection for this line that's leaving this station. So our green is one system of protection, and our blue is our other system. And you can see, like I was trying to explain, one system will tie into this set of CTs right on the inside, and then the other system will tie into the outside set of CTs on the breaker. And it looks like they have a GEL90 relay for one system and an SDL411L relay for the other system. But again, like I was saying, sometimes these are the exact same relay doing the exact same function, exact same protective schemes, and it's really just for redundancy. I guess in the interest of time, I'm gonna maybe skip around and try to zoom through a lot more of this because this one ends up being pretty long. Relay CT and VT requirements vary between voltage levels. Right, if you're at 345 kV versus 115 kV, obviously your ratios are going to be different. Whether you need redundancy at the station, can determine how many CTs you need, right? So lower voltages, we don't really care about redundancy very much. Higher voltages and extra high voltages, you almost always see higher levels of redundancy. Usually in this high voltage range, maybe you don't see two battery banks in the control house, but definitely at extra high voltage, you see every level of redundancy you can think of, everything we discussed earlier. Aux transformers, this is usually like a transformer installed on the secondary circuit of a CT or a VT to maybe change the ratio, maybe for some isolation, right? You don't really see this too much anymore, but again, like it says here, in older stations, they end up being pretty common because sometimes you have weird ratios, maybe lack of CTs, right? So this isolation is important. That's a good way to get some redundancy with only one CT circuit available. Device numbers, we've got some IEEE ANSI numbers. If we go back up to here, you can see that, this breaker control relay is a 79/551. This GEL90 line relay is a 321. This one's 87L. So those all mean something, right? And that's determined by this IEEE standard. It identifies the function. So 87 is a current differential. 21 is a step distance. I think 50 is time over current. 51 is instantaneous. I might have that backwards. I guess we'll find out right now. Oh, I did have it backwards. So 50 is instantaneous. 51 is time. There's a bunch of these functions that usually utilities will put it in the name of the relay, and it gives you a pretty good hint as to what the relay is doing. Bus protection. Usually what you see is a lot of differential protection, but sometimes you do what they call poor means bus protection with just some strictly overcurrent. And all that means is, right, say this is our bus. We have this CT tied into our bus diff relay, this CT tied into our bus diff relay. So it's measuring the current into the bus and the current out of the bus. And if the sum of those is ever not zero, then the bus diff relay will trip these breakers and make sure the bus is protected. And I guess this kind of is going through that. Distribution bus protection. So this would be like a low voltage bus. A lot of the times you don't see that differential, so they'll just measure the current going into the bus, and if that current gets too high, they'll just trip every breaker on the bus. Line protection. Again, I'm going to skip through some of these, but overcurrent, you see that a lot on line protection. Directional, which way the power is flowing. That's another big one for line protection. Direction distance or step distance. Usually what you'll see is if there's step distance protection being used, you won't see differential protection being used or vice versa, things like that. So time over current, what that means is, if there's a fault on the line, after some amount of time that the relay reads that there's a fault, by an increased amount of current going through the CT, it'll trip the breaker and clear the line. Instantaneous overcurrent, what that one means is if the fault level is high enough, the CT reads the fault current or some multiple of the fault current, and if it gets high enough, it'll just trip the breaker immediately. There's no delay in the trip. Directional, this one you need a CT connection and a PT connection so you can tell which way the power is flowing, but the relay should know which way the power should be flowing, with like a load flow analysis or something like that. And if the relay reads that it's flowing the wrong way, it'll trip to clear the line. Distance, this one ends up being a little more complicated, I think. So say you have a line from substation A to B, and let's focus on substation A. You'll have a relay here, and it's looking down the line. And the way it does that is with the impedance of the line, right? This line will have a set impedance. So, if it's 10 miles, say it has, 10 ohm impedance, right? So it knows 80% of the line would be 8 ohms, or 125% of the line would be 12.5 ohms. So it knows how long the line is based on the impedance. So it usually has some zones that it looks at to protect. So the first one would be, this 80% of the line zone. So if there's a fault, if it can measure a fault in this first 80% zone, it'll trip this breaker pretty quick. If it measures a fault in this 125% zone, a little further out, maybe into or past substation B, it might wait a little longer because the relays at substation B might pick that one up first and trip and clear the line before substation A would. And I guess this is kind of explaining the same thing, right? So these 80% zones and the 125% zones obviously overlap, but right over here, right, this 80% zone and this 80% zone, substation B or substation A would be strictly responsible for those and trip before the other one. Line protection differential is pretty much the exact same concept as the bus diff protection. The only difference is you can't read the current on the other side of the line with just regular copper cables, right? So what ends up happening is one relay on one end of the line will read the current out of the station. The other one at the other station will do the same. And then there'll be some kind of high-speed communication between the relays to do the high-speed tripping. There are some other communication schemes such as fiber, but we've got power line carrier, microwave, and fiber, and there are some other tripping schemes like DCB, POTT, DTT, which I guess if I had more time I'd get into, but you'll have to trust me that that those are used sometimes. I guess this is just kind of about some of the other communication schemes. So let's see. Okay, transformer protection. Transformers are usually protected by some kind of relaying scheme, but sometimes they're protected by fuses, right? Where the smaller transformers, the less expensive ones, you just throw a fuse on it. Hopefully the fuse operates properly and your transformer doesn't blow up. But once they get a little more expensive, utilities like to have them protected a little more properly. I guess there's a couple different types of sudden pressure relays. If the oil in the transformers expand too quickly, differential protection on the transformer, same concept as the bus in the line, overcurrent, ground overcurrent, same concepts as the other types. And again, I think I'm just gonna skip through quite a few of these. Yeah, I think we hit the biggest concepts I wanted to hit, just in the interest of time. I think I feel pretty comfortable with that. I guess any questions or comments on Relay One Lines Part 2? Any comments on protection or anything like that? All right, great. Well, Ryan, I think I stole a lot of your time, but I'll let you take it away.
Not to worry, my practice run took 25 minutes. I think I can get that down to 5. Kidding, of course, folks. Let's see.
And guys, I'm going to log off. I've got a baby to go take care of. So if anybody has any questions or anything, feel free to reach out. I'm always available for an email or a phone call or anything. And it's great seeing some familiar faces. Great seeing some new faces. And thanks for your time tonight. Bye, everybody.
Thanks, Jack.
Have a good one, Jack.
Thanks, Jack.
Can everyone see my slideshow?
I will do it. Thank you.
Yes.
All right, perfect. So, hi everyone. I'm Ryan Haskell. Also work for Power Engineers, same office as Jack. Graduated UMaine EET back in 2021, and come up on 4 years here at Power almost. So I'll try and keep this quick so everybody can get out of here in a reasonable time. But we will be covering AC schematics, also known as 3-line diagrams. So AC schematics, these are developed and finalized during the preliminary engineering phase after the 1-lines have been fully developed. And these are developed alongside the DC schematic diagrams and done prior to any detailed wiring diagrams. The purpose of AC schematics, these are essentially to expand on the relay 1-line, offer much more detail, show correct information like phasing for buses, transformers, lines, bushings of breakers. And a very important part is to show the secondary AC connections for relaying. So things like the instrument transformers feeding into the relays. So right here we have an example 1-line diagram similar to what you saw with Jack's presentation. And the section we'll be focusing on is highlighted in the red rectangle there. The 3-line focuses on the section with the 2 breakers and a single line node, which, as shown on this slide, it shows the same equipment, major equipment, broken out into more detail with each individual phase, the bushing numbers of the breakers, the phasing of the line, and most importantly, all the instrument transformer connections feeding into the individual relays. 1-line symbols versus 3-line symbols, they should be very similar enough that you can figure out what you're looking at simply based on the drawing comparison between 1-lines and 3-lines. I believe this bottom section here is from a standard, so it's not filled out with the proper information yet, hence breaker name A rather than a proper breaker name. But as you can see, it breaks out devices such as the current transformers on a phase-by-phase basis and shows wire node labels for future development during the wiring diagrams, during more detailed design. Key thing during 3-line design is around breaker bushing numbering. Bushings are always numbered the same way. It's pretty much an industry standard with bushings 1, 3, and 5 on one side and 2, 4, and 6 on the other. When designing 3-lines, do not mirror the breaker. These bushing numbers are assigned again as a standard and are shown on vendor prints, so manufactured drawings. And if you try and mirror this just to say flip the positioning, say with 1 and 2 being on the bottom here, but 1 on the right, that would imply the breaker is hanging upside down based on the vendor prints. So be careful with that. Continuing with 1-line symbols versus 3-line symbols. The example we have here is a transformer connected to a circuit switcher with a set of surge arresters or lightning arresters between them. And one key thing that people prefer to see when designing 3-lines is to try and follow the same orientation as the relaying 1-line. Here, this is not the case with the circuit switcher being placed on the 1-line on the right side of the drawing, whereas the 3-line shows it on the left side. There's usually a reason for this. There's most definitely a reason for this one. I'm not familiar with this project, so I'm not sure why these were not oriented the same way. but it is definitely something to try. It's good practice to try and keep the same orientation. So it's easier to switch between the 1 line and the 3 line for reference. When putting together a 3 line, it's important to confirm standards, conform to them. Between utilities, there can be a wide range of practices, different symbols used, standardized across the utility, but not between utilities usually. There are some overarching bodies that try and standardize it, but not everyone follows them. And not understanding the symbols can result in a mistake, say using a different type of switch compared to what is actually called for during the design. Say using a manually operated switch rather than a motor operated switch. Phasing, it's very important to confirm phasing between schematic drawings and physical design drawings. The drawing show, or the section drawing shown on the top right here is what we call an EA drawing. It is essentially the physical layout of the bus work and all the other major equipment. And on the bottom left, we have a 3 line, or in this case, it was technically called a bus wiring diagram, but the same purpose. And it is important to do these cross-discipline checks throughout each stage of the project just to make sure the phasing lines up properly. And this can change depending on design choices made throughout the whole process. Continuing on, phasing can differ between substation utilities. One example could be utility A using phases 1, 2, and 3, utility B using phases A, B, and C. I've heard of one utility for lower voltages using 1, 2, and 3, but 1 does not correspond with A. So that's something to confirm when connecting between multiple utilities. And it's also good to confirm design choices along the transmission line. Say, for example, the phases could roll depending on the structure of the transmission line. Continuing on, single phase and 3-phase equipment. Some equipment, such as potential transformers, may only require a single phase, so it's good to confirm which phase is connected to on the physical drawings against PNC drawings, in this case, relay 1 line and 3 lines. Continuing on, here's one example. On the left is this company's example of a 3-line diagram, but with a single phase potential transformer connected only to the A phase, and on the right is the relay 1 line, also showing only an A phase connection. Getting on, here's another example of a phase dependent item, this case being a wave trap for communication over the line and the equipment associated with that for line tuner equipment. As you can see on the left here, the 3 line calls it out on B phase, matching what is shown on the single line diagram. Current transformers, Jack went into pretty good detail on these, so I will skip past these just to save us some time. But a lot of this information will be from the 1 line will be reflected as well on the 3 line. Here's a good example of a CT nameplate. These will, in the case of bushing mounted CTs that are associated with breakers, nameplates will be shown on the breaker itself, listing out the different ratios available for the CTs and on the other equipment ratings of the CTs in this case, such as thermal rating factors, accuracy, and the CT identifiers. Continuing on, CT configurations. CTs can be found in both 3-phase and single-phase configurations. 3-phase CTs can be found on equipment bushings for relaying. Single-phase can be found on transformer neutrals or internal transformer relaying. They can be configured in delta or Y arrangements. Jack already covered auxiliary CTs, but these can be used for isolation or changing ratios beyond the available ratios. Here we got a couple pictures of, on the left, a transformer, and on the right, a circuit breaker. And just to point out, the bushing CTs will be located on the breaker in this structure on each of the bushings, and for the transformer in this structure. Jack already covered up ways to screw up a CT circuit, but this is an important thing to be aware of. Do not leave it open. Connect it to the right polarity. Make sure to have the right connections, series or parallel. Parallel is really a bad description, as Jack said, of the way these can be connected. But definitely make sure the right sequence of connections is followed. Connecting with the wrong CT, that's definitely a big no. And multiple grounds is definitely not something you want with CTs. Here we have an example, a three-line example of a high impedance differential circuit, with this circuit essentially functioning off of the way this circuit functions is each of these CTs are summed up at a central location to keep similar cable lengths to avoid additional impedance. And from there, they are run together to the relay, which due to the high impedance will generate a voltage across the input. And that is what the relay is set to, as far as my understanding of it goes. But it's good to, I believe this was included from the previous presentation, just to point out it is very important to make sure this is done correctly and not have extra length of cable. Otherwise, this relay setup is very sensitive to additional impedances. On the other end of the spectrum, we have a low impedance differential connection, which is just a very simple one-to-one CT to input, limited really only by the amount of CT inputs available on the relay. PTs and VTs, Jack covered this one pretty well, so I'll leave this one alone for now. Generally found in 2 or 3 configurations as well. 3-phase PTs provide potentially using one PT or VT on each phase. They can also be arranged in a broken delta configuration, which allows 3 phases from 2 PTs. This is typically not preferred, but it is actually fairly common in metering setups. A couple of pictures of PTs and VTs. Central one, I believe, actually the station service transformer. FT switches. These are used to isolate relays from current potential circuits. All relays need to be tested before they're put into service. And anytime relay settings are updated, they need to be tested as well. They can be configured into sets, 1 set or 3 sets of switches, each set usually having 10 switches from what I've seen, but not the only configuration. And they can be configured to have different switches for currents and potentials for the sake of isolation, safely isolating relaying. Some clients use different colors for trips and closes. One function of these current shorting, make before break test switches is that when opening up the test switch, it creates a short to prevent, say, a potential from arising on a CT circuit and safely isolating the relay, prevent damage as well. We'll take a quick look at the configuration site for this as well. But this is an example of a set of 3 test switch sets as made by ABB. And they have a wide variety of configurations for these test switches. So they can be customized for each function. Say here we've got 3 current isolating test switches and 4 regular test switches with various colors. But we won't linger on that for too long. PK blocks, these function in a similar way to the FT test switches. They provide ways to isolate relays from current and potential circuits. They require these shorting plates to perform a similar function to the test switches, and they must be installed correctly at the beginning. Secondary connections for AC schematics. You need to ensure secondary winding of whatever piece of your equipment is correctly connected to the relay is the correct rating burden for the relay. And it's very important to verify CT or PT configuration when connecting to a relay. The incorrect configuration can cause a relay to trip or fail to trip. And down here, we've got some ratings of the relays themselves, what kind of burden they provide to the PT circuit and CT circuit. And another couple examples of secondary connections. On the left here, we've got direct bus connections to PTs in a OPA delta configuration. From there, connecting to a relay. Very simple on the left here. And on the right, we've got both PT connections and CT connections from a breaker connecting into a 451 relay, which is typically used for breaker failure protection, from what I've seen. All right, project examples. Before we wrap this up, I got a couple of project examples we can take a look at for 1 lines to 3 lines. This is a previous project I worked on, which involved a 1-to-1 relay replacement for an old out-of-date TPU 2000 relay protecting this reactor on this drawing. So the 1 line here has a lot more equipment on it compared to the 3 line we'll see, but the corresponding 3 line only covered this section of the 1 line, which is shown here. We've got the reactor and an additional piece of equipment shown on another 1 line drawing, breaker 111 here. And as you can see, we've got the phases broken out of the CTs, the PTs, and the actual bus work, the reactors. A lot more detail, but a smaller section of the station overall. And you may notice as well, this follows a different orientation compared to the 1 line, which I'm sure there was a reason behind for this drawing, but this drawing is, before my time. Another project. This one was a overall relay upgrade project. And the section of the 3 line we'll be looking at corresponds to this section of bus on the left here, the 345 kV bus 1, and also includes breaker 851, as well as another breaker shown on the neighboring 1 line. And you can see the same equipment here, broken out by phase, CTs, and all the secondary connections for the relay. And one last project. This one's a bit more unique. That's actually the 1 line Jack was showing on his presentation. This utility, up until recently, did not use traditional 3 lines, or hadn't used them for a while. They instead used what I had called earlier bus wiring diagrams, which split up a lot of the secondary connections onto their own schematic drawings, separate from the 3 line diagram. So this is the overall 1 line. The corresponding bus wiring diagram covered these 3 top breakers shown on this drawing, and the schematic showing the secondary connections reflected these 2 breakers and the corresponding line node between them shown on this drawing, showing all the potentials and CTs, but not really showing the direct connection to the bus wiring diagram. And as far as I know, that this utility no longer uses this setup. They've returned to more traditional 3 lines. But that's that example. And that is pretty much all I have. So if anyone has any questions, I'm open to taking them now.
So I have a question, please. I mean, where did this 1 line and 3 line drawing came from? Did it come from from a textbook or reference book or somewhere
So
else?
these are actual projects we have worked on in the past. Actually, we've removed some of the client information just to obscure it a bit, but these are actual 1 line and 3 lines we've worked on.
Oh yeah, okay. Thank you.
I can also do my best to try and answer some questions for Jack, but he's a lot more knowledgeable than I am.
I got a question about relays.
Shoot.
Yeah, so I guess my question would be like, is there a preferred like brand for like different relays? Like, is there one that's better than the other? Like, I guess in terms of like Schweitzer and GE kind of thing, yeah.
So the most common I've seen are Schweitzer and GE, at least for the utilities I've worked in. A lot of the time, it is actually dependent on company preference. I know of some companies that refuse to do work with GE and vice versa. But it's all really down to preference. They're all, I'd say, is capable. Sometimes a company will use both to offer some sense of redundancy.
Cool. Yeah, thank you.
Yep. Anyone else? All right. Well, if that's that for questions, I think we're all set here. Thank you everyone for your time. And I'll let you get back to your evening.
Thank you.
Yeah, thanks, Ryan. Have a good one.
Thank
You too.
Thank you.
Thank you.